Welcome to the Explainer. So, you're pouring serious cash into GPU hardware for your AI systems, right? Well, you absolutely need to be extracting every single ounce of performance from it. Today, we're taking a deep dive into maximizing the efficiency of your clusters by fixing one of the most silent and honestly most expensive killers of performance: data transfer bottlenecks. We're going to learn exactly how to keep your GPUs constantly fed and constantly computing. Here's our roadmap for today's Explainer: solving the GPU idle problem, Magnum IO and RDMA, mastering NCCL and topology, PyTorch DDP versus DP, and finally, some common multi-node pitfalls. All right, part one, solving the GPU idle problem, which is really the core bottleneck here. Okay, let's dive into this. The absolute fundamental bottleneck in large-scale AI is idle time. You can have literally the fastest GPUs on the market, but their immense compute power is entirely wasted if they're constantly just waiting for data to arrive from memory or disk. When a system handles its host-to-device transfers, then its kernel computation, and then its device-to-host transfers sequentially, just one after the other, you get these massive gaps, just empty idle engines doing absolutely nothing. Conversely, when you use an overlapped approach, multiple CUDA streams ensure that while one stream is computing on the kernel engine, another is already transferring the next batch of data. Everything stays constantly busy. This brings us to a foundational concept: overlapping communication and computation, or, pipelining. It's basically the practice of ensuring data transfers occur concurrently with your ongoing computations. When one task finishes, the data for the next one is already sitting right there. This single concept is the absolute bedrock for building efficient training and inference systems at a massive scale. And the impact here isn't just theoretical. The real-world results are frankly stark. Moving from a serial, no-overlap execution model to an overlapped one, like what's built right into PyTorch's distributed data parallel, yields roughly a 30% improvement in total iteration time. GPU idle time drops to a bare minimum, streaming multiprocessor utilization stays incredibly high, and you achieve this massive overlap where communication is just completely covered by compute. Moving on to part two, Magnum IO and RDMA, the hardware enablers. Let's see how this actually maps onto the physical hardware. How do we get these ultra-fast concurrent transfers without completely bogging down the system? Well, think of traditional data transfer like forcing all your traffic to drive through a brutally congested city center, that city center being your host CPU. But if you bypass the CPU and system memory entirely, you get a high-speed bypass. That's NVIDIA's Magnum IO stack and GPUDirect RDMA, allowing direct memory-to-memory communication between remote GPUs straight over the network interface cards, or NICs. Now, what's really interesting here is the architectural difference. It's huge. Without a direct NIC connection, your traffic has to squeeze through a Gen 5 PCI bottleneck that's connected to the CPU. But with the direct NIC setup, the GPU and the network interface card can talk to each other directly through a PCI switch at full Gen 6 throughput. It essentially allows the GPU to drive network traffic without any CPU intervention at all. It's brilliant. All right, part three, mastering NCCL and topology, our software orchestrator. So we've got these high-speed hardware highways built, but we still need a really smart traffic controller to route the data, right? That's where NCCL comes in, the NVIDIA Collective Communication Library. It's the software that orchestrates exactly how groups of GPUs share data. The most vital feature of NCCL is that it's topology-aware. It acts as the brain of your communication stack. It actively detects whether your GPUs are connected by ultra-fast NVLink or slower PCI, and it dynamically optimizes the routing to keep your data on the fastest possible paths. Just how important is this topology awareness? Well, if NCCL naively forces traffic across a slow PCI interconnect, your streaming multiprocessors might only be busy, say 60% of the time, simply because they're stalled out waiting for memory. But once topology-aware algorithms keep that traffic on NVLink, boom, SM utilization jumps to 90%, and your iteration time drops from 100 milliseconds down to just 70. NCCL manages all this using some very specific routing algorithms. You've got Ring, which is fantastic for optimal bandwidth utilization when you're dealing with very large messages. Then there's Tree, which gives you incredibly low latency for smaller messages because it completes in logarithmic steps. And finally, there's PAT, or Parallel Aggregated Tree. This is a really brilliant hybrid approach. By splitting large messages into chunks and interleaving reduce scatter and all gather phases across different CUDA streams, PAT actually gives you the best of both worlds, near ring throughput combined with tree-like latencies. On to part 4, PyTorch DDP versus DP, looking at framework application. So we understand the hardware and the middleware. But when engineers actually write the code, they usually face a classic showdown: data parallel versus distributed data parallel. DP is a single process strategy, and it's severely limited by the dreaded Python global interpreter lock. Crucially, it gathers gradients synchronously, which totally kills performance. DDP, on the other hand, is the undisputed winner. It spawns multiple processes to completely bypass the GL, and most importantly, it inherently leverages the asynchronous overlapped NCCL techniques we've just spent time exploring. How does DDP pull this overlap off so seamlessly? Well, the magic number is 25 megabytes. That's PyTorch DDP's default bucket size. Instead of waiting around for the entire backward pass to finish, DDP groups computed gradients into these 25 megabyte buckets. As soon as a bucket is full and ready to go, it instantly triggers an asynchronous NCCL transfer, while the GPU just keeps happily computing the next layer. Finally, part 5, common multi-node pitfalls. Let's do some real-world troubleshooting. Now we're out in the real world. You've got the hardware, your DDP code is pristine, but things are still crawling. It's incredibly frustrating, right? Why is your multi-node training so slow when you literally have state-of-the-art hardware? Well, the answers to your mysterious cluster slowdowns almost always lie in a few very common misconfigurations. First up is the back-end mismatch. This is a big one. If you accidentally initialize your process group using the CPU-bound glue backend instead of NCCL, wow, your throughput plummets from 100 gigabytes per second all the way down to just 2. You've completely bypassed your beautiful RDMA networks and maxed out your CPU, dropping your speed by 2 whole orders of magnitude. Always ensure your backend is explicitly set to NCCL. Let's speed through a few more rapid-fire pitfalls. Mismatched NCCL versions between PyTorch and your system, that can cause silent fallbacks to much slower pathways. A narrow local port range can actually cause TCP port exhaustion during the setup phase. If your background NCCL threads get pinned to a single CPU core, it'll totally tank your throughput. Though you can fix that by setting NCCL_ignore CPU affinity to 1. And finally, please never leave a debug statement like torch.tensor.item inside your training loop. It forces a massive pipeline stalling synchronization between the CPU and GPU. So the absolutely crucial point here boils down to one rule: never create and destroy communicators on every single iteration. Initializing an NCCL process group takes a massive cluster-wide handshake. If you put that initialization inside your actual training loop, an iteration that should take half a millisecond can suddenly inflate to nearly 50 milliseconds. Always initialize once at startup. You also got to be super careful with overtuning. I know it's tempting to play with NCCL's million environment variables, but honestly, you should generally keep them at their defaults for production. A totally classic mistake is disabling peer-to-peer copies with NCCL_P2P_disable=1 to debug a local issue, and then just forgetting to remove it. If you leave that active in production, you force all your ultra-fast NVLink traffic right onto the slow CPU path. Which brings us to our final big question. We've seen the mechanics of overlapping, the sheer power of RDMA, and the brains of NCCL. But right now, today, on your cluster, are your GPUs truly overlapping communication, or is your ridiculously expensive hardware silently waiting on some hidden CPU bottleneck? I highly urge you to go profile your environment variables and review your topology immediately. You might just reclaim a massive amount of lost performance. Thanks for joining me on this explainer, and happy optimizing.